Okay. So these two masses are diametrically opposed to each other. They're equal and opposite. So what is the total force? It's just the sum. Right? And if they're equal and opposite, what happens? Anybody?
They cancel out.
Exactly. They cancel out, right? And then we could extend this. So if these two masses cancel each other out, how can we extend this? So what can we say about all the masses that are surrounding us at the center?
They cancel each other out.
Exactly. You could find another pair that's diametrically. You can find another. You can find a pair of masses throughout the whole sphere where they cancel each other out. So at the center, it's zero. What else is interesting is you don't even need to be at the center for it to be zero. Let's say we cut out a larger space. We need more space to hang out here. And we're off to the side in the center. What do you think the force of gravity now is on this person?
Is it going to be very close to zero?
Force of gravity relative to which objects?
What?
I didn't understand.
So we cut out, so this is the Earth. This is what's left of the Earth. It's just a spherical shell. We cut out the core of the Earth, and we decided to hang out here. We'll live here, right? The force of gravity on this person, even if he's not at the center, is still zero. It's exactly zero. What happens is that now we have a mass over here, right? But if we look at it, if we break this sphere up into a section, okay, I have into left and right, let's say, because that's how the symmetry is broken right now, right? You have more mass on the left side of the person compared to the right, right? So you would expect that the person would be attracted to this side, right? But we didn't take into the fact that it's distant dependent, right? So the fact that he's closer to the right side means that the force of each infinitesimally small mass, the force will be stronger, right? Because it's closer to it. And what ends up happening is that these two, the fact that you have more mass on this side, but this will cancel out with the fact that you're closer to the masses on the right side. So they would exactly cancel out with each other, right? So if you inside a spherical shell, no matter how big spherical shell is, the gravity would be zero. If you're at the center of the Earth of the sun, it would still be zero.
So it always has to be a spherical opening in the middle.
Yes, a shell. So it's not. You can't say that it's open. This is a closed surface. Yeah. When you have a cavity like this, it's considered a closed surface, right? Yeah. An open surface would be something like a parachute, where there's no inside to that surface, right? There's no inside to the parachute. You can't define it, right? But if you had one of those rubber balls that you sit in, you see people playing with them, it has an inside and an outside to it. So in that case, it's considered a closed surface. But yes, you're right. I just wanted to clarify what an open closed surface is. But yes, so if you have this closed surface, it would be zero inside. Now, it would be different if this wasn't a sphere, right? Of course, if I added more mass on over here, if I added a mountain over here, we would feel force now, right? And this is due to the symmetry of the problem, right?
What if you cut out a different kind of shape inside instead of a sphere, like a cube?
A cube? A cube would work as long as It's a good question. It would have to preserve the symmetry of the system. So if you had something like this wouldn't work, right? Because now you have more mass on this side compared to that side. So it wouldn't work. I would have to think about it, actually. My first suspicion is that it doesn't matter what shape it is. It would cancel out, but I have to think about it. I can. Let me think about it and get back to you. But in electromagnetism, the same thing occurs. So if you were inside of a conductor, there's no force on that person inside of a conductor. For it's different reasons, but it's a similar principle. And so if you're inside a conductor, it doesn't matter about the shape of the cavity, but the physics is a little bit different here. How it adds up is a little bit different, so I can't say. But
is gravity like a magnetic force? Like, are they similar?
no, it's separate. So there's 4 fundamental forces: gravity, electromagnetism, and then there's 2 nuclear forces, the strong and weak. So they were able to connect electromagnetism and the weak and the strong force. They're able to relate it through equations, but gravity, they're unable to relate it. That's like the last major hurdle in physics, you know, common in pop culture, but they're completely unrelated to each other at the moment. But they should be related to each other somehow. I'll get back to you on the symmetry problem. I'm not sure about if the shape of this cavity matters. Yeah. All right, let's move on. Okay. So where's our launch pad for all the rockets that go into space? Where's NASA's launch pad? Does anybody know?
Is it in Russia?
Kazakhstan.
No. Non-human travel. When we want to launch the satellite, or even now with SpaceX. So where's our launch?
Houston or Florida.
It's in Florida. Do you know why it's in Florida?
Surrounded by a lot of water.
Well, that's one reason, actually. But
Close to the equator.
close to the equator. And why do you want to be close to the equator?
Maximize your horizontal velocity.
It requires less. The escape velocity is less, right? But why is that? Does anybody know?
Because you have the horizontal velocity of the planet as you take off behind you.
Is it?
So the fact that the Earth is moving around, this velocity will help us get off the planet.
Is it because when the satellite, when it's rotating, it's better because, like, remember when we talked about it has no place to go, so it feels weightless, like there's no normal force?
Yes. So why do you feel weightless when you're orbiting the Earth?
Because you have nothing to. There's no reaction for gravity.
Do you still have that? Well, I'm not sure what you mean by reaction.
Like, you know how normal force is a reaction to gravity?
Yes.
Like a table, like there's nothing to push back.
So the fact that you feel yes, we're on the right track. So the fact that we have this normal force makes us feel like we have weight, right? So it's not gravity that makes us feel the force, right? What we mean by feel the force is that our skin compresses on our feet or compresses two parts of our body together, and we have pressure sensors there, and that's how we sense the force, right? It's how we feel weight, right? So it's not gravity that compresses the pads of our feet together, let's say. It's the fact that we also have this normal force also pushing back up. So we have these two equal and opposite forces pushing on each other. And that's what compresses our feet and makes us feel the pressure and feel weight, right? Now, if we didn't have this normal force, we would fall towards the center of the earth, right? And we wouldn't feel any forces, we wouldn't feel the force, right? Because we're accelerating with the force. There's no other force compressing our skin together to make us feel it, right? So in that case, we would feel weightless. We wouldn't feel any of this pressure that we associate with weight. Or you can make the same argument with the fluid in your ears, right? But so the fact that we feel this way is due to these two forces canceling out. And in the end, there's no acceleration, right? It's just these two forces canceling out, and we have ability to sense this, right? Now, in orbit, what happens in orbit, right? Forget about the equator, we're in orbit, we travel around, right? We have the force due to gravity. I'm sorry, my markers are dying on me. I have to order more markers. Okay. We go around the sun like this, around the earth like this, right? So what are the forces on us? Let's say we're going around at constant velocity. There's really just one force on us, and that's the force due to gravity, right? This force, right? But what's so special about our orbit is that we never end up traveling to the center of the earth. Our radius, our radial position from the center of the earth remains constant, assuming that the earth is a perfect sphere. This R remains constant even though we're feeling this force, right? And the reason why R remains constant is because we're experiencing circular motion, right? We're doing this interesting phenomena where if we have a velocity perpendicular to the force, we actually don't move radially. If we satisfy the centripetal acceleration, right? If we satisfy the equation that we learned about last time, right? The force, the radial force, is equal to this. We don't move our radial direction. We keep this distance constant, and we still have this force. So we don't have another force to cancel us out, right? What's occurring is that the force of gravity is the centripetal force, and because of this idea of circular motion, we never go towards the center of R. So we don't have a reactionary force to cancel the force of gravity out to keep us from moving towards the center. We're moving, right? And we're experiencing this acceleration because as we travel along, our velocity is changing. But because it's perpendicular to the motion, we never move in this R direction. We always move, polar. We always move in this angular direction, if you will. Right? We move according to this angular.
So it's only satisfied when velocity is perpendicular to that, let's say, force of gravity in our example, right?
Yes. For
Okay.
this to occur, where R remains constant, we have to have our radial force inward equal to this quantity.
Uh-huh.
And this keeps us from falling towards the earth. We're still moving, right? We're moving in this direction, but we're not moving in this radial direction,
Mm-hmm.
right? Because we satisfy this, right? So we're experiencing the same acceleration, it's just that we're not going towards the center of the earth, right?
The magnitudes of the velocity and this force of gravity, they got to be the same? Or?
No, they have to be equal. They're related to each other through this equation. So gravity has to equal the mass times the velocity squared over r. And this is the tangential velocity. So this is the velocity that's tangent to the motion. So everybody see that?
Mm-hmm.
Right. So we have this force, right? And this, we're experiencing this acceleration, but there's no reaction. There's nothing to cancel it, quote unquote, cancel it out where we would feel the pressure and feel the weight. So we feel weightlessness over here. We don't feel the acceleration. Now let's get back to the original problem, is why do we take off from the equator?
Professor, I'm so sorry. That FR, this is that centripetal force. Right?
Yes, that's the centripetal force, yes.
Okay.
Or more generally, it's a force in the radial direction towards the center.
Mm-hmm. So the magnitude of this perpendicular force, the force of gravity, is not even taken into this equation, right?
It is. The magnitude, my markers are dying on me. The magnitude has to be equal to this.
I'm talking about perpendicular force of gravity in our example. The magnitude of that force is not taken into account.
Yes, it is. It has to, well, it has to satisfy this relationship. That force has to be equal to the mass times the velocity squared over r. Otherwise, this r will change. Not that r. This r will change. This is r. If these two aren't equal to each other, this will either fly out or fly inward until until these forces are equal to each other. See that?
Yeah, I can see that.
So if I slow down over here, I'm gonna if I slow down the spacecraft over here, I'm gonna end up moving further out, right? Because I would have to decrease this force to find the other place where I could go around the Earth or orbit the Earth, where gravity is my centripetal, where I could satisfy this equation. Right? So
if your mass times velocity squared divided by r, if that is greater than the force of gravity, does that mean you're on an escape trajectory?
Greater, okay. Yes, it is. Oh, I'm sorry, I got it backwards. Okay. So what would happen, so if my velocity is greater than the force of, than this force, then I would fly outwards like this. But as I fly outwards, what happens is that my velocity slows down because my r is increasing. You can look at it that way, but there's other ways that we'll look at that in this case. It slows down. What I said earlier, what I meant was that if as you go further out, to satisfy this r, you're gonna take away from this velocity vector and give it to r. So the further out you go, your speed will increase in general. So if you increase your velocity, you will go to a different orbit. You would go out here, say. Or if you slow down, you would go to an inner orbit, right? And what ends up happening, okay, so if I slow down, okay, let me explain it a little bit differently. So if I slow down, if I hit the brakes, right, what happens? I'm gonna go to a lower orbit. But as I go to a lower orbit, to get back into orbit, I have to satisfy this, right? Now R is smaller, right? And F is larger. Because of this, my velocity will increase, right? Now, you have to realize that what I mean by my velocity increasing is that I hit the brakes over here. After I hit the brakes, there's no more force, right? That was the force I applied, a deceleration force right here. Then I don't apply any more force through my thrusters or any other way, and I go down to a smaller orbit. This will increase my tangential velocity to get to the smaller orbit. So I hit the brakes over here, I naturally move down. As I move down, my velocity will increase over here. Right. Think about like when you spin a ball on a string, right? As it gets closer and closer to the center, right? It goes faster and faster. Right. That's what I was talking about before. So when I said when you speed up when you go to low orbit, what I mean is that once you apply the brakes and you start drifting down to this lower orbit, your spacecraft is going to automatically speed up, right? And the reason for that is because as you go down to a lower orbit, you're gaining actually velocity. You're converting this gravitational force into an actual acceleration of the craft. It's actually a very complicated system, this phenomena over here. But so yeah, so that's what happens when you change your orbits. So this brings up a good problem. So let's say if we have a craft, let's say if we want to catch up to a craft, right? So let's say we're at the same orbit. Let me get another pen. Okay, you can see that. So let's say if we're at the same orbit, right? Because we're at the same orbit, we have to travel the same speed, right? How do we catch up to the spacecraft, right? Because if we go faster, we're adding more velocity, and we're gonna travel further out, right? We're gonna change our orbit, right? So catching up from one spacecraft to another is not very straightforward, right? So what will happen is that we would need to change our orbit, right? We speed up, we change our orbit to up here, we catch up to a certain point, and then, we catch up to a certain point, then we start slowing down, and then slowly we'll approach this other object. So we have to use the fact that any object at a certain distance from Earth has to travel at that particular speed. And it ends up being that the mass doesn't matter.
Wouldn't you lower your orbit to catch up?
What?
Wouldn't you lower your orbit to catch up?
But you would have to lower your speed. So if I reduce my speed, that means I would travel this direction automatically. So I can't.
Yeah, but
I can't. Okay, so I can increase my speed in this direction, and travel this way. and travel towards it. If I do that, then I know what you're saying. You're saying basically take a shortcut, right? So instead of that, just increase the speed in this direction, and then you'll catch up to the spacecraft, right?
Well, no, actually, I was talking about how when you said when you boost your orbit, your velocity starts to decrease. So wouldn't you fall behind?
When I boost my orbit, no. Because what's happening here is that, hold on, get out my notes. Yes, I'm sorry. I mixed up the problems. Yeah, of course. Based on what I was saying, we would have to lower the orbit. By lowering the orbit, we would increase the velocity to satisfy this equation, right? And then we would catch up. Then we would have to come back in the other way. I apologize. I got one thing mixed up, and
Yeah, no problem. I was just confused.
yeah. I was actually looking at a problem where they want to slow down the first one, so they sent this up, and then I mixed up the two. Apologize. All right, yeah. So you would speed up, go to a lower orbit, and then you come back out to the larger orbit. That's correct. All right, so let's get back to our original problem that we were going to do. Was why do we take off from the equator as compared to the poles? To figure this out, let's look at the forces, right? So if I'm standing over here, what are the forces on us, right? There's two forces. There's gravity, and then the normal force. And here we'll call it the weight force. Because if you're standing on a scale, the force that the scale measures is not technically the gravitational force. It can be, but in general, it's the normal force that you measure. This marker sucks as well. Okay. So it's this normal force. Over here that we'll call gravity, right? Now, if we stand over here, what are the forces on us? The forces are the same, actually, right? We have gravity, and then we have our normal force, which we'll call Fw, or the weight, our weight, right? So what's the difference between these two circumstances? So up here, let's write out the force equation now. Up here, what will happen? So if we write out the force equation, right, it's just the net force. If are we moving at this point? No, right? How are we moving in this problem? We're moving with the Earth. So the Earth rotates, right? But at the North Pole, we don't rotate, right? There's no rotation. So the net force is going to be 0. And that's just going to be Fg minus Fw. So the normal force is just equal to Fg. Over here at the equator, because we're rotating with the Earth, there's a centripetal acceleration associated with this motion, right? So for us to keep our radius constant, we need the forces to be equal to the centripetal force, to our equation for the centripetal force, right? And then in this case, it would just be Fg minus the weight. And what we find when we solve for the normal force, we find that it's just equal to gravity, so minus what the centripetal force would be, right? So because we're moving around the Earth, we're rotating around the Earth, right? And our radius keeps constant, we have to satisfy, there has to be a centripetal force. And this is the centripetal force, and it's equal to the difference between the gravitational force and whatever force that's keeping us from going to the center of the Earth, right? And that's the normal force, right? So what this is essentially saying is that we're using part of gravity for a centripetal acceleration, right? And then the rest of that force for gravity, we're using as our weight, right? If we were traveling fast enough, we wouldn't need any of this normal force to keep us from going towards the center of the Earth, right? But we'd have to travel pretty quickly for that, right? Which we can easily calculate, if we know gravity, and then we just set this equal to each other, and you can figure out what speed you have to travel on the surface of the Earth to satisfy centripetal acceleration.
Professor.
Yes.
I have a question for you. So on our orbit of the Earth, all the satellites, they maintain this centripetal force, right?
Yeah, they satisfy this equation.
Mm-hmm. And how they do that, because I don't think they run in engines constantly. It's like they push themselves once, and then this Newton's first law works, that the speed remains constant because there is no friction or air resistance. Oh, that's nice. It's nice to learn physics.
So you could calculate this. So how do I have to take off? What's the speed I have to take off? And the direction. And then they can calculate this trajectory so that once it gets to a certain height, it will enter into this orbit like that.
Mm-hmm. Nice.
And it'll naturally do that because it would slow down accordingly as you take off from this. As you take off from the Earth, you enter the sideways trajectory, and then as you go up, you'll start to slow down in one direction, and it will naturally enter orbit. And then there's of course some corrections. You have thrusters that you could change your orbits with, and stuff like that. But the general, you don't need that much force to change your orbit. You could actually calculate it, how much force you need to use to change your orbital heights. So.
Thank you.
Mm-hmm. So it's really cool, and it's just a simple equation that's used for space travel. It's of course more complicated because there's a lot of extra terms they have to take into account, like relativistic things you have to take into account, and so, and that's it. And then so what happens is that the normal force is less on the equator than it is at the poles because you have to use it for centripetal acceleration. And it's very, very small. So the change in gravitational constant between the equator and the polar coordinates, it's about 0.03 meters per second squared, right? When gravity is 9.8, so normally 9.8, this is less than 1% lower, right? Or about 0.3%. Yes.
Can we say if something is flying, let's say next to the Earth, and it can just enter the orbit if it's flying at the proper angle?
Yes, it can. Yep.
Yeah.
Neglecting air friction, of course. Well, it doesn't even matter about air friction, but yes, it's just impossible to keep that velocity if you consider air friction,
Okay.
air drag. But yes, it would be possible. So let's calculate what let's just calculate what the centripetal acceleration would be, right? So what is our velocity if we're at the equator? How do we calculate the velocity? The velocity is just distance over time. So if we rotate around, if the Earth rotates, completes one full cycle in 1 day, right? That's our time, would be 1 day. And what's the distance that we travel in one full rotation? Anybody?
Just have to rearrange. It's a V times time.
Yes. So it would, the distance that we travel one full rotation is just the circumference. It's just 2 pi r divided by 1 day. And our velocity that we travel at is, when we in terms of meters per second, is about 4.6 to the second, 10 to the second meters per second. So we travel about 460 meters per second around the Earth. That's how fast we're rotating with the Earth, right? We don't even notice it, right? Well, you can't notice it. Now, let's do another problem. So for a lot of these orbits, so you always hear the term geosynchronous satellites. What does this mean? Anybody? Does anybody know what a geosynchronous satellite is?
They probably move as the Earth moves, like rotates.
Yes, it rotates the same speed as the Earth, right? So that means its tangential velocity is what we just calculated, right? So its velocity would have to equal or I shouldn't say its velocity because it'll change at the. So